Hello, we're going to look at example 22, and it says to prove for all values of n in the element of the positive integers that n cubed plus 5n is a multiple of 6. So we're going to go through it. So the first step, piece of 1, we want to check that since we're in the positive integers, we know that 0 is not a positive number, so we're not starting at 0. We got to plug our value in and see if it's a multiple of 6. So I'll go 1 cubed plus 5, right? 1 cube's 1, that is 6, and 6 is, obviously a multiple of 6. So I can say, so piece of 1 is true. Good. Now, piece of k is the step where we assume our statement right up here that k cubed plus 5 times k is a multiple of 6. And we can, just like we did when we had a divisible, it's the same difference. We can say 6a, and we have to set restrictions on our variables so we know what we're talking about. The easy part is k. We could pretty much just use what we have up here. We can use what up there, so k has to be in the element of the positive integers. And we want a to be any integer. We just don't want any decimal points, right, to show that it's a multiple. So, and say a is in the element of the integer. Sorry about it, got a little messy there, but just an integer. Good. It could be negative, positive, but as long as it's an integer, it can be 0, whatever, and so on. So now, now we can use that later. Then we do the case of k plus 1, piece of k plus 1, right? What I want to show is that k plus 1, I basically plug it in to my expression up here, is also a multiple of 6. So I have to use a different letter. I don't want to use the same letter, so I'll go b, but then I have to state that b is in the element of the integers as well. Good. And like now I got to move this guy over and show that it's a multiple. So I'm just going to expand this out. Here I can just, if you remember, you can expand it out by hand, but I remember Pascal's triangle for this one. So this is going to expand out to k cubed plus 3k squared using these coefficients right here, plus 3k plus 1 plus distribute this through 5k plus 5. Good. Simplify this a little bit. I'm going to have k cubed plus 3k squared. Got some like terms here. 8k plus 6. Now I can use my, well, I don't have this guy to make it 6a. I guess I could try to make it that way, but the easiest way is just to solve this expression like we did in the previous problem. So I know that k cubed is equal to 6a minus 5k. Good. And now I have a substitution. So I can go 6a minus 5k plus 3k squared plus 8k plus 6. And let's see, what do I have here? I'm going to have 6a plus 3k squared. A negative 5 plus 8 is plus 3k plus 6, right? Good. And then I can see I can factor out a 3, and I got 6a plus 3. And what do I have? K squared plus k plus 2. Now you might think that doesn't factor, and it doesn't, but what we're looking for is just to make this a multiple of 6, and it's not quite there yet, right? But if I look inside these two expressions, I know I can change this to, sorry, let's move down so you can see what's going on. But anyways, I go over it again, so this doesn't factor, but if I look right here, these two guys do. So 6a, all I'm doing is to confirm that this is a multiple of 6, and something different happens in here. I end up, if I factor out that k of just these two expressions, I get k plus 1 plus 2, and then there you go. Now, the trick is right here. What kind of a number is this always going to be? We'll look at those. I'm going to have k times k plus 1. Whatever that value is, those are what we call consecutive integers. And what kind of numbers are consecutive integers? Like 1 times 2 is 2. 2 times 3 is 6. 3 times 4 is 12, and so on, right? These consecutive integers, when you multiply them, is always even, right? Since that's always even, I can write this expression. Therefore, I can write this expression k plus 1 has to be equal to something at 2 times some other value. So we already use a and b, so I'm going to use c in the element of the positive integers, right? And then I can use the substitution, right? I know that's going to be even, so I can use this to help me. So I go 6a plus 3, then it's going to be 2c plus 2. Distribute the 3 back through, and I get plus 6c plus 6, and then I can see 6 is indeed a factor, so it's a plus c plus 6, and I've showed what I wanted to from the beginning of the k plus 1 step. So there you go. We had a little bit of trick with this type of thing, and this can happen in a lot of different ways, you know, so kind of look for it, especially with problems like this, when you have to find multiples, or even divisible by multiples or divisible by. You can end up thinking you're stuck, but you know, don't forget that consecutive integers are even numbers, and when you multiply them, and you can reformulate it this way. So, and then I finish it off with my statement. Therefore, if piece of 1 is true, and piece of k is true, implies that piece of k plus 1 is true, then the statement is true for all n in the element of the positive integers. Make sure not to leave anything out. All right? Sound good? There you go. Oh yeah, and I almost forgot. Whenever you prove something, mathematicians like to put that little QED at the end. I don't know if you've looked that up yet, but there you go.